All right, so we're beginning chapter 4, which introduces some number theory, and will be a chapter that some teams will look into in greater detail when they study cryptography for their project later this semester. So, the topics that we're going to study in this section, just in the first few in this chapter, in the first few sections, these topics are sort of like some of the like the basic stuff that underlies cryptography and some of the modern methods. But I think you'll find that these subjects are interesting and useful to programmers in general for other reasons besides just like computer security and that kind of thing. So a lot of what we're talking about here is going to be quite fundamental to like algebra. And in fact, some of what we'll get into at the end of this section relates to a course, like a course you could take maybe in the next couple of years at a four-year university called Abstract Algebra. It really kind of gets into the nitty-gritty details of like, well, what are, how do integers work? How do how do the operations work? And, what is division and like prime numbers and that kind of thing. So, all right, let's go ahead and get started. First thing we're going to do is define something, divisibility of integers. When we say that one number, and by the way, we're going to be dealing with integers almost exclusively in this chapter. So if I ever forget to say what a number is, assume it's an integer. So if one number a divides another number b, what that means is that the second number b is a multiple of a. And that multiple is represented by this letter k in this definition here. So that would be b is equal to ak for some integer k. Now, this might sound kind of familiar because this is essentially an extension of the definition of an even number that we talked about way back in chapter 1. We introduced this idea that an even number is a multiple of 2. So this is essentially, in the terms of divisibility, you could say an even number is one for which 2 divides that number. Okay, 2 divides any even number. And the notation that we use for that is this vertical line. This character here is called a pipe. It's used for a lot of different things. In programming, sometimes this unit means or, I believe, but we use it in this context here to mean A divides B. So let's look at a couple of examples. So 2 divides 6. This is true because 6 is a multiple of 2. Now, you may be used to seeing something like, a fraction bar, like a horizontal fraction bar, and this, a little bit confusingly, this is closer to saying 6 divided by 2, right? Usually you put the thing you're dividing by on the right-hand side of the fraction bar, okay? So some students will get this notation confused with this, but this means a different thing. This is not a fraction. This is saying that 2 can divide the number 6 evenly, right? 6 will go into 2 a whole number of times. So 2 divides 6, 2 is also going to divide 8, and so on, right? Remember, 2 divides any even number. So 2 would not divide 7. And so you can use the pipe character and put a slash through it if you want to say it does not divide, right? 2 doesn't divide 7. 7 is not a multiple of 2. What's another example? 12 divides 48. Sure. 5 divides 45. Sure. Things like that. Now, here are a couple of general rules. There's a couple of things that you always have. In general, a number a is going to divide a multiple of a. So if m is any multiple, a divides ma, right? Just because m suffices for this k value, right? K could equal m. I could have used a k right here instead. So that's true for any number m, including 1. So in particular, every number divides itself, all right? 5 divides 5. 17 divides 17, because it is itself times 1. It is a multiple of itself. It is the 1 multiple of itself. So that's always true. Another thing that's always true is that this m value here could be 0. So in the definition here, k could be 0. right? So you could say that A divides 0 for any A. This is a little bit of a strange thing to say because this looks like, again, don't get this confused with the slash for division. You're not saying divided by 0. This is more like 0 divided by A. A can divide 0, and that, will yield an integer value. It'll yield 0. So that is valid. Any number divides 0. And then the last thing to say is 1. 1 divides any number, because any number is itself times 1. And so that's so there's a couple things that are always true. Now the book introduces a few theorems about divisibility. I just want to go over one of them that I think kind of sums up a few other ones. This is kind of like taking all the theorems and putting it into one. And it says this: if A divides B and A also divides C, so we have a number A which we are assuming divides both B and C, then what we can conclude is actually that A divides any what's called linear combination of B and C. So that would be basically where you're taking the B and the C and you're creating a little linear expression using B and C by multiplying the B and the C by other numbers that are called M and N here, and then adding those together. So, and this is for any integers M and N. So this right here, this is any linear combination of B and C. The term linear combination is one that comes up quite a lot in some areas of mathematics. Another area of mathematics where you'll deal a lot with linear combinations is linear algebra. I bet you might have guessed this is all about algebra or somewhat related to algebra, and it's linear. So yeah, if you take linear algebra with me next year or in the fall, then we'll talk about those a lot. So just as an example of that theorem, say 3. Let's take the number 3. 3 divides 9, and also 3 divides 12. So I can take any linear combination of 9 and 12 and be guaranteed that 3 will divide that. 3 will divide, for example, like I could do 9 times 2 plus 12 times 3. I could do something like that, which is, this is saying 3 divides, oh gosh, what is this? I didn't actually do this arithmetic in advance. 12 times 3 is 36 plus 18, so 54, unless I made a mistake in my head just then. And 54 should be a multiple of 3. What's 54? It's, I don't know. It's late. 54 should be a multiple of 3. So there's an example of a theorem and how to apply it to something simple. We're going to dig into a lot of the things. We might not actually use that specific theorem, but I just wanted to give you an idea of what you can do with this definition.